Hello, this is Adam Ward, and I want to provide one extra example related to our lecture number 7, which is on diffusion, the first foray into incompletely mixed systems for our class. In this example, we're going to consider a bay that's connected to an ocean. Notice that bay has no inflows of surface water to it. So flow through from the bay is not a process that we'll consider here. However, in our bay, we've noticed that we've got a concentration of 10 parts per billion of a particular pollutant. Now, because we don't have any visible inflows here, we're going to assume that pollutant comes from a relatively low discharge but high concentration outfall. So a very concentrated release of that pollutant into our well-mixed bay. We've got a bit more information about the bay. We know its cross-sectional area. We've got the diffusion mass transfer coefficient that describes exchanges between the bay and the ocean, and we've got the mixing area for the bay and the ocean. Our objective in this problem will be to find the loading into the bay that's causing this 10 parts per billion concentration that we retain at steady state. Now, one thing that I want to point out here is that concentration profile as it moves toward the ocean. You see it taper off to 0. This is called the infinite sink assumption. The idea here is that the ocean is so large that the small amount of concentration that will actually make it to the ocean has a functional concentration of 0, or will never increase the concentration of the ocean. This may not be true for all species, but for the particular pollutant we're considering today, let's assume that it is. I'll show you where that assumption plays out in a moment. So on the right-hand side, the solution for our problem, let's write out our typical equation for the bay describing its accumulation as a function of loads and removals. Here you can see the only load we're considering is W, the mass loading rate into the bay that we're interested in finding, and the only mechanism that we have for our pollutant to leave the bay is through diffusion. And so you've got that capital E prime there, that's the bulk diffusion coefficient multiplied by the concentration of the ocean, subscript O, and the concentration of the bay, subscript B. Moving on, we'll make two key assumptions. The first is that the system is at steady state, so the left-hand side of our equation becomes 0. And the second is that infinite sink assumption. So we'll consider the concentration of the ocean to be 0 at all times. We can rewrite our equation then. It looks a little bit simpler, although still not something that we're quite ready to solve because we're missing that bulk diffusion coefficient. You'll remember from lecture that the bulk diffusion coefficient can be related to the diffusion mass transfer coefficient by the few equations shown here, where that capital E over L, the mixing length, can be replaced by the diffusion mass transfer coefficient V sub D. And that's what we were given in this problem. So when we make that substitution into our equation, we can also isolate W by moving those terms to opposite sides. And we end up with this equation. Now from here it's just putting in the numbers and solving. So we plug in our known diffusion mass transfer coefficient, our known cross-sectional area, and the concentration of the bay. And you'll notice here that we were given concentration in 10 parts per billion. I'm just substituting in milligrams per cubic meter because those are units that are going to lend themselves a little nicer to ending up with a mass loading rate where we want a mass per time as our final units. So you could stop right there. I'm going to add in just a couple of unit conversions to get this into some units that are a bit more meaningful, kilograms per day, and I find a final solution of 80 kilograms per day as the loading rate into the bay.